Okay, so now we're going to the last section of this chapter, which is all about energy conversion efficiencies. Now, what do I mean by that? Well, it's simply saying how well are you using the energy you have to do what you actually want to do. For example, I could write this as saying efficiency is equal to my desired output over my required input. And if I wanted to have a real life one, it would be like a water heater. So for example, this water heater has electrical power going in through the top. So that would be some sort of energy electricity. And that is going to here and to here, and there are two resistance bands or two resistance coils in there that are heating up your water. As a note, they don't actually look like that. Typically, they just look like a big, long U. How do I know that? I had to replace mine. Now, the electrical energy that's going in there goes through this resistance coil, and that goes into heat into your system. And so I'm trying to figure out the efficiency of this water heater. I would say, well, that's equal to, in this case, the amount of heat that actually gets into my water over the electrical energy that I was putting in. So if I knew that value, I could figure out the efficiency of my water heater. And electrical water heaters are actually fairly efficient. They're about 90% to 94% efficient at heating up the water using that energy. Now, that is a bit misleading. I'll go ahead and tell you that they're really, really efficient at getting the electrical power to heat because it's just one component. It's a resistance. So almost all of it will always get there. Like that's the true for all resistance heaters. You have a whole lot of energy that goes straight to heat. But that doesn't mean it's cheap. It takes a lot of electrical energy to get that heat going. And also, if you don't have an efficient hot water heater, it will lose a lot of heat over time just because of convection and radiation and other things. Another thing to think about is that gas, while it's not as efficient at getting the heat from like the flames straight into your system, because some of it gets convected other places, it is often cheaper because you can, one, heat the water very, very quickly. So sometimes you'll have instant hot water heaters which are heated when you need them, so you're not keeping the water hot when you don't need it. And two, gas is just cheap in most cases, so it's sometimes cheaper to use that. Now, if you can use electric, go electric, save the environment. But realize that the electrical power that you are using is also being produced by the burning of fossil fuels, most likely. So either way, try to conserve energy as you can. Now, that was just one type of efficiency. And there's a lot of them. Like I can go from mechanical efficiency, which is simply saying what is the mechanical energy input or mechanical energy output. And this can be electrical, it can be heat, it can be all kinds of things going into it to make it do this, to figure out what it is. So that'll be my mechanical efficiency. I see that a lot when it comes to like pumps or turbines. I'm trying to figure out how much of the energy output, what fraction of that energy input is that. And remember, this is always going to be less than 1. It can never, ever be more than 1. This cannot be more than 1. That's the wrong way to write that. It cannot be more than 1. There we go. That's better. Another one is simply saying, I have electrical efficiency too. I didn't actually mention that right here, but these electrical devices, which would be energy in to energy out. For any particular like converter or other things we might have, like transforming devices, that would be equal to 1 minus my energy in over energy out. And the note here, that's pretty much the same equation every single time for all systems. What's your energy input? What's your energy output? Take the ratio, and you can figure out where you're going with it. Okay. Now, I have a pump here and I have a turbine. These are two things that if you go into applied thermodynamics, or Thermo 2, however you want to call it, you're going to see them a lot. And so you're trying to figure out how efficient a pump is or how efficient a turbine is. Well, both of them are trying to do two things. One, the pump is trying to increase the energy of your fluid. And so you have to ask yourself, well, how much energy is my fluid gaining and how much work was I putting in? For a turbine, you're trying to use energy from the fluid to output work. So how much of the fluid's energy were you able to do that? And if you look at here, you'll notice that these are exactly the opposite. If we're saying, well, wouldn't 1 be less than 1? That wouldn't be more than 1? No, because I can't just magically connect a pump to a turbine and say it's going to go on forever. I'm going to lose energy both ways. I can't get all the energy back out of the fluid to make work. I can't get all the work to put energy into the fluid. So it will constantly be losing energy as I go through the cycle. Now, let's look at a more complex case. So right here, I have a generator, and I have that connected to a turbine. When I am calculating efficiencies, it's never just the efficiency of one component that I care about, like just the turbine or just the generator. I need to know how to calculate those. But more than that, I need to know what the efficiency of the system is. What is the efficiency of the system? And that requires that I take the efficiency of each individual component and I multiply them together. So I've got this turbine generator system. Its efficiency is equal to the efficiency of the turbine times the efficiency of the generator. And when I do that, I can get my overall efficiency for the entire system. Okay, everybody, I think we'll stop there for this time. Thank you so much, and we'll finally finish this chapter in the next video. Have a good one. Bye-bye.